Okay, so we're going to be calculating crystallographic symmetry with AFLOW. And so this is done with the AFLOW symmetry module, appropriately named AFLOW-SYM, and it determines the invariance of a crystal under transformation. So for example, it finds the mirror planes, it finds the rotation axes within a particular crystal that when you perform the operation, it maps the atomic positions back onto themselves. And so with these symmetry descriptions, we can find things like the space group, the Bravais lattice, the conventional cell, the Pearson symbol, Wyckoff positions, primitive cell, and many other different symmetry descriptions. And so why is symmetry important? In particular, it's used throughout the entire AFLOW code. So for example, we've already seen a little bit with the Brillouin zones that Corey mentioned in session 1 and the K-paths. So these are symmetry dependent. And so we need to know what the symmetry of the crystal looks like to determine the Brillouin zone and also these high symmetry K-paths. In addition, once we get to, I think on the last day for phonons, we actually see that we use symmetry to, one, plot the phonon dispersion, but also to reduce the cost of simulating these phonons. And so it only determines unique distortions based on symmetry. And so Marco will probably talk about that a little bit in his talk. We also use it for prototype generation and classification. So we'll see this tomorrow morning, where actually, if we want to label a particular structure, we typically refer to its symmetry characteristics. And finally, since we have this large AFLOW database, we want to characterize all of these materials by their space group, Pearson symbol, and many different symmetry attributes. And so since symmetry is used throughout these different analyses, it needs to be very, very robust. And so as Cormac mentioned earlier, we have over 3.2 million entries in the AFLOW database. And so AFLOW-SYM works for all of these entries with no human intervention. And so basically I want to highlight how we've been able to achieve high consistency results without the need to have a human basically playing with parameters to get consistent results. So to illustrate this, I want to show how do I identify a particular symmetry element in a crystal. So for example, let's say that we have this arrangement of atoms. So we see this diamond here, diamond shape or geometry of atoms. And we want to know whether or not it has fourfold symmetry. So if you were to rotate these atom positions by 90 degrees, do they map back onto themselves? And so there's 3 possible scenarios. So if we perform the rotation, there are 3 scenarios. One is when we perform the rotation, we map exactly back onto the same positions. And so this would be considered a map. And so this symmetry element would correspond to this structure. On the other end of the spectrum, when we perform the operation, maybe there aren't any atoms there. And so we can see here that in this case, this would be a 2-fold rotation, not a 4-fold rotation. So rotate by 180 degrees instead. So this is not a map. However, the more common scenario is this middle one here, where maybe the atom positions don't exactly map back up when we rotate the atom positions. And so the question is, should these map? And so this becomes a tolerance question. Since we're working with we're working with real numbers, and we want to know whether or not these positions are equivalent, symmetry equivalent. And so typically, we use a tolerance threshold, so maybe a radius epsilon, that'll signify when these atoms map back onto one another. And so in general, to determine whether or not we have a symmetry in our crystal, we need to compare the original atom positions to the transformed atom positions after we've performed the rotation. And if we compute all of these pairs, so we compute the distances, and all of them are less than this epsilon, then we consider all of the positions mapped, and the symmetry is observed in our crystal. But since we're working with crystals, and I think Corey mentioned this earlier, is that we're typically representing our structure via a small subunit. But we need to consider the fact that it has periodic boundary conditions. And so we need to consider the method of images. Another thing that we need to keep in mind is that we need to be careful when we're performing mappings in non-uniform metric spaces. So what do I mean by this? So on the next slide, here we see, I'm going to illustrate this problem. So let's say that we have a cubic lattice, and we're in Cartesian coordinates, so with these global coordinates, and we have a tolerance sphere, epsilon, representing whether or not we can map atoms. And so we want to see how the space changes when we're working in fractional coordinates. So if you remember, for all of the postcards, we were working with direct or fractional coordinates. And so essentially we're performing a basis transformation. And so when we do this, if we're in a cubic system and we perform the basis transformation into fractional, anytime we represent something in fractional, it's a unit cube, regardless of what the lattice looked like beforehand. And so when we do this for a cubic lattice, we see that we get this uniform compression of the system. However, if our starting system was orthorhombic, when we convert to this unit cube, we see that we have this non-uniform compression of the space. And so we see that the sphere is actually an ellipsoid. And that's because the space is being compressed when we perform the transformation. And finally, if we have a triclinic system, then we get the shearing of this sphere, and it turns into the sheared ellipsoid. And so what this tells us is that distances in Cartesian coordinates look differently in fractional coordinates, and they can become direction dependent. And so we need to be careful when we're performing mappings. And so here's an example. So on this right-hand side, we see mapping consequences. So here we have a 2D crystal. And let's say we want to know whether or not this crystal has a mirror plane along this line here. And so to do this, we perform the transformation. So we consider all of these hollowed spheres as when we transform these blue atoms into these orange hollow spheres. And so to determine whether or not this is a mapping of the crystal, we need to perform a minimum distance calculation between the original blue atoms to the symmetry transformed orange atoms. And so we need to consider the method of images since we have a periodic crystal. And so we see that the minimum distance to this atom is this neighbor here. And so we call this DC min. But typically when we do this in fractional coordinates, so there are actually other codes throughout the community that actually perform this minimum distance calculation in fractional coordinates. Excuse me, so again, we need to perform a minimum distance calculation, but if we're doing this in fractional coordinates, remember our space is warped. And so we've converted any object into this cubic object. And so if we do the minimum distance calculation, we actually see that we get different results whether or not we calculate it in Cartesian or fractional. And so this can be really problematic when you're trying to find symmetry operations automatically and that are consistent. And so the takeaway here is that a minimum distance in fractional is not necessarily the same in Cartesian coordinates. And AFLOW-SYM takes this into account. And so it takes into account the lattice skewness. So that's one way that we get high consistency results. The other way is that we have a self-consistent tolerance scan. So to show this, we have this particular system. And so this is actually a real example where we calculated the space group symmetry of a particular crystal. And we changed the tolerance value. So here we have a tolerance number line from 0 to 1. And so we calculated the symmetry at different tolerance values, and we evaluated the space group symmetry. So we would observe that for tighter tolerances, we observe lower symmetry, so monoclinic. And then for looser tolerances, we observe higher symmetry, so space group 225. But the question is, what happens in this void region here? And so this can actually happen where maybe the symmetry calculator identifies inconsistent symmetry results. So for example, if you're familiar with crystallography, maybe it found 49 point groups, which is impossible based on crystallographic convention. And so instead of throwing an error or trying to figure out what operation to throw out, AFLOW automatically performs this tolerance scan, where at the tolerance value that found inconsistent symmetry, we perform a radial tolerance scan outward and continue to calculate the symmetry until we find consistent symmetry at a new tolerance value. And so this is an automatic way to calculate symmetry. And the other thing I want to highlight is that our software uses system-specific tolerance values. So if you use others in the community, they typically have predefined preset tolerance values, maybe 1/100th of an angstrom for any system that they encounter. However, AFLOW considers each system, and it considers the minimum nearest interatomic distance and scales that by certain scaling factors. And so with these, we can find system-specific tolerance values that will give us consistent results. And so again, this alleviates the burden to a user to determine what tolerance value they should use. And so your next logical question might be, well, okay, so there are these other symmetry packages. How do you compare to the others? And so here we've done a benchmark where we took inorganic crystal structure databases entries, and we compared the calculated space group from certain packages and compared it to the experimentally determined space group. And so here we plot the mismatch. So when experiment and calculation didn't agree. And so we analyzed it for certain packages. So FineSym, if you're familiar with that, Platin, and SPGlib. And so the taller these bars, the worse they are at capturing the space group with respect to experiment. And so you can see that AFLOW performs the best regardless of what lattice type we're looking at. So it had the fewest number of mismatches. And we even changed the tolerance for some of the other packages. So we used their default tolerances for these solid bars, but then for these dashed, we changed the tolerance for the other packages. So maybe we scaled it by a different factor. And so you can see that you get some change of the results, but this shows that if you're using these other symmetry packages, you really need to play with these tolerances by hand. And so it can become a burden on the user. However, with AFLOW, this is done automatically, and our tolerance values give you the best consistency space group results. So this is just an example. Okay, so I've highlighted some of the technical details of how we calculate symmetry. And so now I'll briefly highlight what different symmetry elements that we might be able to calculate. So if you're familiar with group theory or crystallographic symmetry, we can calculate point groups. So these are the rotations, inversions, and roto-inversions that when you apply to a point that leave a fixed point, and if you rotate about that fixed point or invert about that fixed point. So here's some examples to the side here. So this shows a twofold rotation. So we're rotating about this axis, and then we go here, and then we rotate back to the same spot if we apply it twice. Alternatively, here's a sixfold, and so it generates 6 points. This is an example of an inversion. So we have an inversion center, and we invert the points, and you'll notice that it also changes direction. So this character is upright, and then downward after inversion. There's also roto-inversions. So that's shown here to the right. And so here this is a sixfold roto-inversion. So we rotate to this point here, and then we invert about this center. So we go from, I don't know if you can see my mouse, I hope you can. So, but you rotate here, and then you invert about this point, and you get to this point here. And again, you apply it 5 more times until you get back to the same point. So this is an example of a roto-inversion. Okay. Oh, sorry, the slide's going back on me. So this is point group operations. But then if we consider translational invariance, then we get even more symmetry operators. So we get screw and glide planes. So here with screws, we're performing both a rotation and a translation. So this is a twofold screw axis. So we rotate 180 degrees and translate in the Z direction. And then we translate again here. And so here's a threefold screw axis, and then also with different translations. And so if we consider the entire set of this, then, oh, sorry, my slides keep going back on me. Then we get what is known as the space group. So this is basically when we combine the point groups and the and translational invariance. And so we get the 230 space groups. And one important other group that I want to mention is this factor group. And so we can actually perform a coset decomposition. So if you're familiar with group theory, we are essentially taking out a normal subgroup. So here we're taking out the lattice translations, and then we're representing all of the other symmetry elements. So essentially we've partitioned these space group elements into what's inside the cell and the lattice translations represented by this IT. And so what this isolates is that anything that's not this IT is confined within the unit cell. And so this essentially gives us the symmetry that's confined to the unit cell. And so one thing I want to mention, a subtlety, is that if you consider these coset representatives, so these R's, R2 and T's, these do not form a group. So this is just a subtlety. And so again, this is something that AFLOW takes into account, all of these different subtleties with respect to group theory. And so this is just a brief overview. And so knowing this, there are many different symmetry groups that AFLOW calculates. So we calculate the lattice point group. So these are the point group operations with respect to lattice points. And then we also consider the Brillouin zone symmetry, so the reciprocal lattice point group. Then I mentioned the factor group. So this is the unit cell symmetry. So this includes internal translations and rotations and other point group operations. We have the crystallographic point group, which describes the symmetry of the crystal lattice spaces. Then if we take the dual of this, this is the symmetry of the irreducible Brillouin zone wedge. So I think Corey mentioned the irreducible Brillouin zone wedge, and this is the corresponding symmetry description. There's also something known as the Patterson symmetry group. So this is similar to this here, but we include inversion symmetry. So they're centrosymmetric. We also have space groups. And then finally, there's this atom site point group. And so this is when we have the origin centered on a particular atom and what are the rotational symmetries. And so we'll see this is important for phonons in a later session. Okay, so another analysis that we can perform is that we can consider the crystal spin symmetry. So for example, let's say we have this crystal system here. And if we analyze its symmetry, it has space group 229. However, if we add in the magnetic moment, so again, if we have spin, we can actually see that if we have spin up on the corners and spin down on the center, that this can actually break or lower symmetry. And so in general, the crystal spin symmetry will be a subgroup of the crystal symmetry. And so if you're familiar with VASP, I know we did an introduction today, but VASP also has a symmetry calculator. And so this is an analysis that they perform as well. So this is analogous to that analysis. And one thing I want to mention is this is not the same as the magnetic point group, because that includes time reversal symmetry, so spin flips. And so that's something that we're looking into for the future, but at the moment, we just consider crystal spin. So AFLOW provides many different representations for the symmetry elements. And so here, this isn't an exhaustive list, but we provide many different representations. So for example, we provide the different symbols for the symmetry operators, the transformation matrices in Cartesian and fractional coordinates. We provide Lie algebra, axis angle representations, also quaternions, and then also atom mappings that specify what atom indices map before and after the symmetry operation. We're also consistent with the Crystallographic Standard. So if you're familiar with the international tables for crystallography, we can determine the standard space group label, the Wyckoff, or the space group setting, and the Wyckoff positions, which are site symmetries for particular sets of atoms. And so it relates the different atoms in your crystal that are related by symmetry. So we do have some functionality online, and I think I'll go ahead and show that now. So I'm gonna exit here. So you can feel free to follow along if you open a browser. And so if you open a browser and go to aflow.org, hit enter, I'm going to see if I can zoom in a little bit. There we go. Okay, so if you're on our AFLOW website, if you scroll down, you can go to AFLOW-Online. So that's this button here. If you click on it, then we have an online interface where you can upload your own structures, and then you can perform various analyses. And so we'll actually see this throughout the workshop for different modules that we'll be talking about. And so in particular, I want to draw attention to the symmetry. And so we have a preloaded postcard. And if we want to determine the space group, so this here, it's new AFLOW. If you hit enter and submit, then it will determine the space group. So right here. So this is the label and the space group number. And so there are a few different symmetry analyses that are available online. So you can feel free to explore this during the exercise session. But I'm gonna focus more on the command line and Python interfaces throughout the rest of the session. And so in addition to this, so we have the online functionality, but then also you can visualize the symmetry operations on each of our entry pages. And so we briefly went through how you can go to an entry page, so I'll do that now. So again, we'll go to aflow.org, scroll down, we'll go to the Mendelib search, and let's look for the rock salt structure. So sodium chloride rock salt. So for now, we're just going to do Na and Cl. We're going to restrict the species to 2, and we're going to hit search. And so we want space group 225 for rock salt. And if we click on this, it should take us to a particular entry page. And JML may take a second or two to load. But if you scroll down a little bit, you can see that we have symmetry operators right here. And so if we want to visualize some of the symmetries for this crystal, I'm going to hit this background supercell. And let's say we wanted to look at this C2 rotation. So we'll highlight the rotation axis, which is along this direction here. And then we're going to rotate the crystal. And if we rotate it, we see that it mapped back onto itself, but outside of that unit cell. And if we apply it again, since it's a two-fold rotation, we map back into our original position. And so this is very useful. So for instance, if you want to visualize the symmetry, or if you're having trouble knowing what axis the symmetry axis is along, or maybe you're teaching a class and you want to show this. But one thing that is useful, I'll show another symmetry element, is it can actually help us to understand the different symmetry elements. So I'm going to scroll down until I find a roto inversion. So S3. So here, this is a rotation and an inversion. So we'll show the rotation axis. Actually, I'll pick a different one. I think I want to show a better one. There we go. Okay. And so we'll also show the point of inversion. And so if we apply this, since it's an S3, you might be thinking that after you apply it 3 times, since it's a threefold inversion or threefold rotation, after the third one, you'll be at back at the same spot. But that's not the case. So if we do it, we apply once, invert, so we're here, apply it again, 2, we're not in the cell yet. If we apply it a third time, we're actually not in the same spot again. And so we need to apply it 2 times as many as you might think. So 6 times, 4, 5, and 1 more. And that will bring us to the same cell. And so this is actually a subtlety that I ran into. I was confused why after 3 operations, it didn't map to the same spot. So again, this is a very useful tool to show exactly how these symmetry operations work in a real crystal. Okay, so you can view all of these online for all of the entries on AFLOW. And so that, this is a nice feature that we recently added. Okay, and so I'll go back to the presentation. And so I think I actually have a movie here that shows a 4-fold rotation. Okay, and so last for the presentation portion, I just want to highlight a particular use case of why symmetry is important. So we've already seen a few cases, but here's an example where we use symmetry to reduce the expense of a phonon calculation. So for example, we need symmetry to, 1, determine the Brillouin zone. So again, we're looking at the k-paths for our phonon dispersion. But we also use it to determine which atom sites are equivalent so we can find certain distortions. So here is a particular distortion that we would model to build our phonon dispersion and for our phonon calculation. And so if we're using a robust symmetry analysis, we can actually reduce the cost. And so here's an example. So if you're familiar with other packages in the community, there's Phono3Pi, ShengBT, and ours is AAPL. So this is the anharmonic phonon calculation. And so you can see that because of symmetry and robust implementation into the APL software, we actually get a reduction of the number of static calculations we have to perform compared to our competitors. And we have similar accuracy. And so this is just a particular use case where symmetry is important. Okay, so now I'm going to show you how you can actually use the AFLOW-SYM functionality. And so in addition to the online interface, you can also use command line, and we also have a Python module. So if you work with Python, you can easily integrate this into your framework. Okay, so I'm going to open the portal. So I'm actually going to move this, and I'm going to get the PDF version so we can see it better. I guess any questions up to this point before we start the exercises? Okay, it looks like maybe no questions right now. That's okay. Okay. So if everyone can follow along with the portal. So again, we're going to be using the terminal. So I'll try to go a little slower for those not familiar with it. So I'm going to exit out of here. I'm going to open a terminal. And I'm going to increase the text size a little bit. Okay, hopefully people can see that. And if I can grab the screen, there we go. Okay, so again, make sure that you have the AFLOW module loaded. So module load AFLOW. Okay. All right, so make sure you're in your desktop. And again, we're still in day 1, AFLOW day 1, and we have to cd into the directory. And now we are in 03. So cd 03 AFLOW symmetry. Okay, so we have quite a few exercise directories. And so we're going to be doing all 8 of these together, and then we'll split off to do the exercises in our breakout sessions. So let's cd into directory 1. So cd1, tab for autocomplete, and hit enter. Okay, so ls into the directory. And let's cat the README. Okay, so based on the slide and what the README says, we want to determine the space group symmetry. And so we want the space group number and symbol. Then we're going to determine the Wyckoff positions. So these are the atoms that are related via certain site symmetries. And then we'll calculate many different symmetry descriptions with this sgdata command. So let's do this. So, so here's a more, if you look at the README, here's just basically, no surprises here. We're going to tell you exactly how to calculate things. So if we do ls, we see that we have a rock salt postcar here. So to determine the space group, we do AFLOW minus AFLOW capital SG, and we are going to direct an input file here. And so in this case, we have MGO. And you can use tab for autocomplete and hit enter. And so in this case, as you might expect, if you're familiar with the rock salt structure, it's space group 225, and this is the international label. If we want to determine the Wyckoff positions, you can use the ycar command. So AFLOW minus ycar. And again, we're going to pass in the geometry file. And if we enter, and so this created a ycar. So it's similar to a postcar, but it's placed the atoms into representative Wyckoff positions. So here we can see we have this designation ycar. We see that the lattice vectors are actually given in a slightly different notation. So this is A, B, C, alpha, beta, gamma. This is space group 225, and this is the setting. And I'll talk about this number in the next exercise. And so here we see we have magnesium and oxygen, and it also tells us the Wyckoff multiplicity, so 4. And so this tells us that in the conventional cell, there are 4 magnesium atoms. And then we also have this designation. So this is just an arbitrary label for this particular position that's given by the international tables for crystallography. And then finally, this is the site symmetry associated with this site. And same for the oxygen. So, but what if you wanted to have more space group information, such as different label conventions or more descriptions? So you can use this, or you can determine this with the AFLOW minus sgdata command. So if we do this, AFLOW minus sgdata, and we're going to pass in the postcard, hit enter. And so we actually have quite a bit of output. So I'm going to scroll up. Okay, a little too far. Okay, so this is SG data, which stands for space group data. So it gives us the space group number, the Hermann-Maguin designation, the Hall designation, the Schoenflies, the Lau class, crystal class. Then it gives some information with respect to the international tables for crystallography, different setting and origin choices, the general Wyckoff position, if you're familiar with that. And then again, we saw the representative Wyckoff positions. And finally, we've expanded out these Wyckoff positions. So I said that there were 4 atoms, 4 magnesium atoms in the conventional cell. And so we've expanded these out by the relevant site symmetry, and we've generated these 4 positions. And so this is the conventional cell. And so for those who like Python and might want to work this into their Python workflow, we also have a Python module. So I'll show the module at the very, very end of the session, but I'll at least show you how you can use it. So if you do ls, you should see example.py. So we'll go in here, example.py. And again, I'm going to do :set no wrap. Okay, so what we need to do first is, if you're familiar with Python, we're loading the particular Python module. So that's what's going on here. And then we're importing the symmetry module. So there's a file called AFLOW-SYM.py in this directory, and there's a symmetry class. And then this is just another library. And so to run a similar method or a similar analysis via the command line, you can do this with Python by opening the file, instantiating the class, and specifying the path to the AFLOW binary. So you need to have AFLOW installed on your machine. And then you can run this get sgdata function. And then you can print out the output. So let's do :q, and let's run this Python script. So if we do Python example.py, hit enter, it's going to return a JSON. And we can see that we get similar analyses from the SGData. So we have the Wyckoff positions, but they're all formatted into this JSON object. And so this is nice because if you pass this to a JSON reader or back into Python via Python dictionary, you can actually manipulate these attributes. So for example, going back to this Python script, I'm going to comment out this line, and maybe we just want to print the space group and the Wyckoff positions. And so if we do this, Python example, and so now we see that the script performed the analysis and we were able to grab the certain relevant properties based on the keywords. So this is just an example. So you can either use command line or a Python module. So any questions about that so far? About getting the space group symmetry information? Okay, so it sounds like hopefully everyone's following along so far. So that's the space group symmetry. And so here I've shown the output in the slides, so you can look at that for your reference. But now, in the international tables for crystallography, generally there's only one setting, so there's only one convention, if you will. However, for certain space groups, there may be multiple settings. So for example, if you have a rhombohedral space group, you might represent the system with respect to the rhombohedral coordinates or the hexagonal coordinates. Or if you have monoclinic, then you might have unique axis B or C. Or if you have a centrosymmetric space group, then you might have two different origins. So you would have the origin on a high symmetry site or the inversion site. And so you can specify which one you want to use with the setting command. And so it's aflow -- sgdata -- setting, and then you put a number. So let's go ahead and do that. So to do this, we're going to go into the second exercise directory. So we're going to cd up one directory. We're going to go into directory 2. And we're going to cat the README to see what we're going to do here. So we're going to calculate the space group for the different setting choices. So again, I highlighted that there are 3 particular examples where you might change the setting. And so we're going to print the Wyckoff positions for each of the subdirectories that we've done, and we're going to change the setting. And so we're going to run this command here, aflow -- ycar -- setting, and a number. And the numbers correspond to the particular cell choices here. So they're also in the slides here for reference. Hopefully you can see that. Okay, so if we ls, we see there's 3 directories. So you can feel free to follow along. We're going to go into the first directory, so the centrosymmetric. So there are 2 postcards in here. So what we're going to do is we're going to run the ycar command. So aflow -- ycar. Then we're going to specify the setting with -- setting equals, and we're going to do both. So for centrosymmetric, there's 1 and 2. So 1, and then we're going to pass in, let's do beta cristobalite first. Hit enter. And so here, we see that we've created the y-car and we specified setting 1. And so for setting 1, the origin is on the high symmetry site. And so if we look at the Wyckoff positions, actually the silicon atom is on the origin. And so the site symmetry is the high symmetry site that we're talking about. So it's this -4,3m. And the inversion site, which happens to be oxygen, just in this particular case, is slightly offset from the origin. But if we run the same command, so if you're familiar with the terminal, you can just hit up on the arrow and you'll get the previous command. So this will be very helpful when we're doing multiple exercises. So if you hit up, and then if you go back and modify the setting, you can go back and change the 1 to a 2. And now you can see that we have a new y-car, but now we've done setting 2. And you can see that actually now the origin is on this site, which happens to be the inversion site, and silicon is now offset. And so you can play with these. And so just to show, I don't know if people are familiar with the space group settings of the ITC. So here's the space group diagram. Hopefully this is just a detail. If you're not familiar with the diagram, that's all right. So, but here we have origin choice 1, and this is actually space group 227. So the exact example we were looking at. And so origin choice 1 is on this high symmetry point here. So you see this very complicated sphere. So this is the origin, and then offset slightly, represented by this very small dot, this hollow dot, that's the inversion site. And so we can see that again, we're able to match with the international tables for crystallography, which is essentially the standard for crystallography. Okay, so that was centrosymmetric space groups, and we can do the same thing for rhombohedral and monoclinic. So let's go ahead and do that. So CD. So let's go to the rhombohedral directory now. LS. We're going to do the same command. So AFLOW -- ycar -- setting equals 1. So for rhombohedral space groups, looks like it froze for a second. For the YCOP, the setting 1, it should be the rhombohedral setting. And I think my computer froze. Hopefully you can still hear me also. But.
Still hear you.
Okay. All right, I'm going to cancel it, try running it again. Maybe it just got stuck. Thank you. I forgot the input file. Thank you very much, Umair. Hopefully I'm pronouncing that right, but thank you very much. Yes, it needs an input file. So we need to direct MG, or in this case, we're doing Caswell-Silverite. And so if we direct that, we see that we have the rhombohedral setting. And so this is indicated by 1. And so for rhombohedral, if you're familiar with the difference between rhombohedral and hexagonal, the rhombohedral cell is 3 times smaller than the hexagonal cell. So if we run setting 2, so again, if you hit up, you can get the previous command. And now we're going to do 2. And now you can see that the cell is slightly different. So you can see the parameters look different compared to before. And also the Wyckoff multiplicities, so it tells you the number of atoms in the conventional cell, they've been tripled with respect to the hexagonal cell. And so this shows that we've changed the setting for this particular space group. And finally, we'll go to the last example for this one, monoclinic. So again, we're going to do AFLOW -- ycar -- setting equals 1. And thank you for the reminder to add in the input file. So this is actinium, setting 1. So this is for monoclinic. So setting 1 indicates unique axis B. So we can see that this is A, B, C, alpha, beta, gamma. And so B is 9.23 and beta is 105.81 degrees. But if we do the second setting, so hit up and do setting 2, we see that the Wyckoff positions look the same, the coordinates are different, but now we see that this 9.23 is in the C-axis, and that actually now gamma is not 90 degrees, as before it was 90 degrees. And so this, again, shows you that you can transform settings. So does that make sense to everyone? Any questions about the space group settings? And feel free, I don't know if I'm going too fast or too slow. I'm trying to go a little slower for those who aren't familiar with the terminal, but if I'm going too slow, feel free to use the go faster button in the Zoom chat. But okay, so now we're going to move on to the next type of analysis. And so this is what we call the extended crystallographic descriptions analysis. And so this will give us things outside of the space group, such as the Pearson symbol, the lattice type, and many different other descriptors. So let's go to the new exercise directory. So we have to go up 2 directories. And now we're going to go into folder 3. Okay, so let's look at the README. So in this particular exercise, we're going to determine the symmetry descriptions for the Weberite or Weberite structure. We're going to determine the Pearson symbol, the Bravais lattice type / variation for the crystal, the lattice, and then we're going to determine all of the possible crystallographic descriptions that AFLOW can perform. So, and here are all the hints, and the hints are just the commands. So let's go ahead and do this. So ls. So we are going to first determine the Pearson symbol. So that's AFLOW -- Pearson. And we're going to direct the Weberite structure. And we see that we get the Pearson symbol. And so if you're familiar with what the Pearson symbol tells you, it tells, this O says that we're in the orthorhombic crystal system. We're body-centered orthorhombic, so that's what this I means. And there are 44 atoms in the conventional cell. So if we just look at what is in this structure, so if we cat the postcard, this is a somewhat complicated structure just looking at it, but we've been able to determine the Pearson symbol, and it tells you information about the conventional cell. Okay, so that's the Pearson symbol. If we want the lattice type, we do AFLOW -- lattice _ type, and we're going to direct in the Weberite structure. And this tells us, again, what the Pearson symbol alluded to was that it's orthorhombic, body-centered orthorhombic, and then also the lattice variation. And so I'll tell you a little bit more about lattice variations in the next few exercises, but this has to do with when we're trying to determine the Brillouin zone and the different, the definition, this characteristic becomes important. And so if we want all of the possible crystallographic conventions that AFLOW provides, we'll run eData. It stands for Extended Crystallographic Data. So AFLOW -- eData. And we are going to direct in postcard. And it'll take a few seconds because it's calculating all of the possible symmetry descriptions. And so hopefully I can scroll through and see everything. Okay. So hopefully people can see, but so it determined the lattice parameters here. So that's at the top here. We've determined the Bravais lattice of the crystal, excuse me. So we can see it's orthorhombic, the Pearson symbol, crystal family, the different point group symbols. So Hermann McGueen, Schoenflies. It also gives us the space group information as well. So this is space group 24. Below this, and then also the Wyckoff positions with respect to the ITC standard. We have the y-car, so we've expanded out the Wyckoff positions. And then we also have the Bravais lattice of the lattice. So these are the lattice points, so no atoms in the crystal. The superlattice, which tells us if we were to, again, this idea of decoration, decorating a particular structure with only one element type. So in this case, we see that we have 4 different elements. But what if they were all the same element type? That will change the symmetry. And so in this case, that's what this superlattice indicates. So equally decorated, and that's why it's said here. We have the reciprocal lattice information, reciprocal lattice symmetry, and finally we have different representations of the crystal. So Corey alluded to this idea of having a standard primitive and standard conventional cell representation. And so here we print out the standard primitive representation, and then we also have the standard conventional, which is twice as large. And so again, for those who like Python, we also have a Python module. So if we open the Python script, we can do a similar analysis. Again, we've seen this before. We're opening the structure, instantiate the class, and then we're going to run this eData function that we've made. And so we're going to exit out, :q, and we're going to run the Python script. So Python example. And so again, it might take a second or two because we're performing many symmetry analyses. And now we can see that all of this eData information that we saw before is now in JSON form. And so again, you can easily integrate this into your workflow if you're using Python, and you can use the Python keyword or the Python dictionary keywords to grab certain attributes. Okay, so I think that does it for the extended crystallographic description. We'll go out one directory. And so in the slides, I've given the eData output for reference, but we've already seen this. Now we're going to talk about converting geometry files. Okay, so that will take us to directory 4. So if we navigate in here, and we'll cat the README to see what we're going to be doing. Okay, so we're going to convert the magnesium oxide rock salt structure into the following forms. And so first we're going to do ABC car. So this is exactly just like a postcar, but what we're doing is we're converting, instead of this 3x3 matrix, we're converting it into this 6x1 representation here, where this is alpha, or sorry, excuse me, A, B, C, alpha, beta, and gamma. So the different lattice parameters. So let's do that now. So if we do, okay, so if we do AFLOW, so here I'm going to use this cat instead. So we're going to do cat MGO, and again, we're going to use the pipe convention, AFLOW -- ABC car. And if we just hit enter, then we can see that we have this different representation. And then we've already seen the Y car, but we'll just do it for good measure. So if you hit up once, and you can modify the file, we'll do AFLOW -- Y car. We've already seen this. It shouldn't be a surprise, but it's space group 225, and we see the Wyckoff designations here. And so again, if you're looking at the slide, this gives you the representative Wyckoff coordinate, and then also the Wyckoff multiplicity, letter designation, and the site symmetry. And again, you can use the setting functionality as well. You can also convert the structure into the different standard primitive and standard conventional. So if we're looking at the README, there are 2 types of primitives. One is the just a normal primitive, so it won't take into account a symmetry analysis. It'll just try to primitivize the structure. So again, we'll do AFLOW minus prim, and we're going to redirect the MGO. And we see that it's in the primitive structure. And we can also, if we hit up, and if we put S prim, which stands for standard prim, this takes into account a symmetry analysis. And it determines the representation. And you can actually see that it is not very different than what we had before. It just happened to change the scaling factor a little bit. But if we were to convert these, they would be the same. If we want the standard conventional, we hit up, and then instead of S prim, we're going to put S con. If we do this, then we see that since this is face-centered cubic, it's 4 times the primitive cell, and so we have 4 times as many atoms as well. And so those are all the conversions to different representations. So I guess so far, any questions there with the different conversion techniques? And so I guess maybe why is it important? So typically for VASP calculations, we want to convert to a primitive representation. So in the first exercise, Corey showed that the time difference between the conventional versus the primitive. So it looks like somebody just asked, what are the different conversions for? So this is one example. So if you want to run VASP, you typically want a smaller representation. And so for the aluminum, FCC aluminum example, when we did the conventional cell first, it took a little bit longer for the calculation to converge since we have more atoms in the unit cell. But if we convert to a different, smaller representation, which is completely equivalent, we didn't change the crystal at all, we just changed the representation, then we can reduce the number of atoms and thus reduce the cost of the simulation. Alternatively, maybe for certain calculations, for example, in phonons, sometimes it's better to start with a conventional representation as opposed to the primitive. So maybe you want a more orthogonalized representation. And so it really depends on what simulation you're trying to perform. But the main point is that AFLOW has many different conversion techniques. So hopefully that answers your question.
I can add to the phonon calculation pane. When you have a primitive cell and you have a very elongated primitive cell, and you create a supercell that you need for phonons, VASP might not be able to convert your structure because the structure is just so weird and elongated that VASP has trouble figuring out what's going on and getting the structure to converge. So a conventional cell actually helps when it's more orthogonal for VASP.
Yes, yeah. Thanks, Marco, for elaborating. Yes, so yes, it really depends on what your application is, but yes, there are advantages to using certain representations over another. So, so for conversions, so now we'll move on to symmetry operators. Excuse me. All right, so we're going to go up one directory. And now we're going to go into folder 5. So CD5, symmetry operations. And so let's see what we're going to be doing here. All right, so there's quite a bit of output, but let's look at the slides first. So I mentioned before that there are many different symmetry operations that we may be interested in. So for instance, the point group operations, the factor group or unit cell symmetry, the site symmetry, or maybe the space group operations. And so AFLOW can calculate all of these different descriptions in one go with this command here. And so before we run it, what will happen is AFLOW is going to create a few files. And so they're listed here. And so this is what the files will be written to and what they contain. So it'll be the lattice point group, crystallographic. I think I mentioned this in the slides earlier, but all of these analyses are written to these files. We also support 2 different formats. So if you use this format, commands, so minus minus print, you can use human readable text or JSON. So again, for those who like Python, you can easily convert this to a JSON and then convert it to a Python dictionary to perform subsequent analysis. So let's do that now. So we're going to run the command. So it's AFLOW minus minus AFLOW-SYM. Again, it's case sensitive, so this SYM is capital. We're going to pass in MGO. And so one thing I want to point out is this is rock salt and it's the standard conventional cell. And so we'll hit enter and it's going to print out a lot of output. And so if we just scroll up, it's kind of hard to see since it's bunched up here, but this might look familiar in the AFLOW VASP runs. And so this is the output that's in the lock file. So this is just an abbreviation of the different symmetries. So let's look at the files. So again, they're XZ compressed. So again, which is good for saving space. And so let's look at some of the files. So let's first go into aflow.pgroup.out.xz. So this, again, I'm going to use set no wrap. Okay, so at the top, we see the number of point group operations. So since we're in aflow.pgroup.out, this is the point group operations with respect to the lattice points. So we're not considering any atoms, we're just looking at the lattice grid and what is the symmetry of this lattice. And so there are 48 point group operations. And so I mentioned earlier that AFLOW provides many different representations. And so for example, so for this first operator, this is the identity. And so it's, the type is P group, we have the type is the identity or unity, the Hermann-Magouin symbol. And actually I'm gonna go to a more exciting one than the identity. Let's go to this mirror operation. So this is a roto-inversion type symmetry. Hermann-Magouin symbol is M, Schoenflies is S. This is the rotation matrix in Cartesian coordinates, the rotation matrix in fractional coordinates, the matrix generator and SO3 expansion coefficients. So this is Lie algebra, if you're familiar with that. Then we also have SU2. So this is, again, some more Lie algebra, but it involves complex numbers. We also have the axis angle representation. So this is a mirror. And so it's analogous to having an axis here and then an angle, and then the quaternion vector and matrix. So again, this is related to Lie algebra as well. So that's for point groups. So if we do :Q, and then so we have many different point group operations. So we have point group K Patterson, point group K Xtal. So point group K Xtal is the point group of the crystal. So let's open that. So vi aflow.pointgroup _ Xtal. So actually we're going to do Xtal, not K Xtal, which would be the reciprocal. So here, again, we also see it that there's 48 point group operations. So again, it gives us a similar thing. We'll exit out of here. I'm going to go to the factor group now. aflow.fgroup. Set no wrap. So here we see that we have more factor group operations. So why is this? So I mentioned briefly at the beginning that we're using the magnesium oxide rock salt structure in the conventional cell. And so again, the factor group gives you the symmetry with respect to the particular unit cell. So in this case, it's the conventional cell. And so we have 4 times as many operations because of the relationship between the primitive and the conventional cell representation. So if we were to run the primitive, we would see that it'd be 194 divided by 4, so 48. And so with the factor group, we have the point group operations, but then we also have these two here. So this is the translational component. So we've added translational symmetry, and C tau is the Cartesian translation, F tau is the fractional translation. So this one isn't very exciting because it's no translation. But here, for instance, we see that we have a translation along 0.5 in the x direction and the z direction. And then we also give the mapping information. So this tells us what atom indices map to which after the transformation. And so there's a lot of information that, depending on what you're doing, you can actually manipulate this, and you can use it to whatever use case you might have. And so this is one case where, for the phonons, again, you're using a lot of these different representations and mapping indices to reduce calculations. And so I won't go through all of the all of the output files. A lot of them look the same, but they're just with respect to different point group analyses. And so, but one thing I'll show you is that you can change the format. So we'll do AFLOW minus minus AFLOW-SYM. And now let's do JSON. So minus minus print equals JSON. And again, we're gonna redirect the postcard. Again, we see this, we're doing the analysis again, but we now see that instead of .out, they're .json. And so we'll just look at one, aflow.pgroup.json. And so there's no spacing, so it's not formatted, but it is a valid JSON. And so again, this is easier to handle for manipulating post-processing. All right, so :Q, and then of course, we have to have the Python example as well to show. So if we look here, vi example.py. So here, again, you do the same type of importing of the module, open the postcard, instantiate the class, and then here, the function is get symmetry. And here, by default, it's gonna do the JSON format. But here, I'm just, instead of printing out all of that JSON to the screen, I'm just gonna count the number of operations, excuse me. And then I'll show one example factor group operation. So we'll close and we'll run the script. So Python example.py, if I can spell Python correctly. And so again, it'll take a second. And so here, if we scroll up, we see, again, a summary of the number of operations. So there's 48 point groups for the lattice, the reciprocal lattice, the crystal, the dual of that crystal, the Patterson symmetry, the factor group, point group for centered on certain atom sites, and then space group, basically the number of operations out to a given radius. And then here's an example of the mirror operation that I showed earlier. And so somebody asked a question, can I use the lock property to keep both files, the JSON and text? Okay, so that's a good question. So in this case, the lock file is really only for running DFT AFLOW. So I guess if you want to do that, I think by default it overwrites it because I don't think I implemented a version to do write both. I'd have to look into it, but I guess, yes, you would have to maybe save it in one spot and redirect the output to another place. So it is a good question, but unfortunately, we're not using the lock property here. But yes, good question. So I guess any other questions up to this point? So about the symmetry elements. So one thing I want to mention is that all of these analyses are done sequentially. And so, as I mentioned, we have this adaptive tolerance scheme. So let's say, for example, we're doing the analysis and we're halfway through, and then we realize we get inconsistent symmetry results at that particular tolerance. So AFLOW will employ this self-consistent tolerance loop, and it'll recalculate everything. And so what's nice is that all of these descriptions are self-consistent with one another. So they all obey the same crystallographic principles, and there's none that will break. And so if you're using other symmetry packages, this isn't necessarily guaranteed. And so this is, again, an advantage of using AFLOW-SYM over some of the other off-the-shelf options. Okay, so symmetry operations. So I went through some of the files. So again, these are here in the slides for your reference. All right, so now speaking of tolerance, let's say you want to change the tolerance, because right now we've just been using the AFLOW default tolerance values. So let's go up one directory to, oh, I skipped something, sorry, crystal spin. So actually directory 6. So we navigate in here. So I mentioned in the slides that if we consider the magnetic moment, we might change the symmetry because we're using spin as a feature to break symmetry. And so we can analyze this crystal spin symmetry by specifying the magnetic moment. And so I'm going to go to the slides quickly just to show that there are actually a few ways you can specify the magnetic moment. So you're going to use this magmom flag, and you can set it explicitly by setting the magnetic moment value. And so AFLOW will automatically detect collinear or non-collinear based on the number of inputs. And alternatively, if you are working with VASP, then maybe you want the symmetry analysis to read the in-car. Since we've shown that you can use the in-car and specify the magnetic moment, if you pass in the path to the in-car, it will digest that information and perform the symmetry analysis. Alternatively, maybe you finished a VASP calculation and you want to know what the symmetry is after the relaxation and what the spin is. And you can also specify the path to the out-car. And so in this case, I've only shown how you can explicitly set it, but actually tomorrow, we're going to be seeing crystal spin again, and I'll show you how you can specify the in-car and out-car paths and how that works. But for now, let's just specify it explicitly. So we're going to do two symmetry analyses. One is we're going to take this body-centered cubic chromium structure, so BCC chromium. We're going to do no spin, and then we're going to add antiferromagnetic ordering. And so we're going to do the space group analysis and specify the magnetic moment. Okay, so to do this, let's make sure we have a postcard here. So crbcc.postcard. So we're going to run AFLOW minus AFLOW capital SG. We're going to do no spin first. And so we'll do crbcc.postcard, hit enter, and the space group, as expected, it's BCC, and so it's space group 229. Now let's add the magnetic moment. So we're going to hit up to get back to the previous command. We're going to do minus magmom for magnetic moment equals, and we want to do antiferromagnetic ordering. And so actually, before we do this, let's actually see what the postcard looks like, because we need to specify the magnetic moment for each atom in the unit cell. So here there's 2 atoms, so we need to specify 2 magnetic moments. So going back to this command, so it's AFLOW minus AFLOW SG minus magmom equals, and then we'll do antiferromagnetic ordering, -1, and then it's comma separated by atom, and then 1. So this is antiferromagnetic ordering, hit enter, and we see that we've lowered the space group slightly. So we no longer have the body-centered nature, we just have the primitive-centered. So space group 221 and 229. And so let's say that we have, we want to consider antiferromagnetic ordering. So, non-collinear. So we need to specify the magnetic moment in the X, Y, and Z directions. So let's say we have, again, antiferromagnetic ordering. So -1, and then 0, 0, and then again, 1, 0, 0. And so what this says is that we have spin along the x-axis and then no spin contribution to the y or z. And so there's 6 inputs. And so AFLOW is going to automatically detect that this is non-collinear. And so we see that, again, we have this lowering of the space group. Well, let's say you mistyped and you only put 5. AFLOW will give you an error and it'll say that it couldn't detect whether or not it was collinear or non-collinear. So it's going to count the number of inputs that you have. So that's how you can perform the crystal spin analysis. Any questions there? Oh, there's also the Python example again. Python example. Again, similar procedure. Open the file, instantiate the class. We're going to use get SG data. We did no spin at first, and then we specified the magnetic moment in the input. So magmoms equals 1 and -1. So antiferromagnetic ordering. We quit and run the script. We see the same results that we had if we did via command line. So any questions there up to this point about crystal spin or anything we've covered so far? Okay, so now we'll actually get to the tolerance. So we have a few more exercises and then we'll be breaking out into the final session, the breakout sessions to do more exercises. Okay, so symmetry tolerance. So we're going to move up one directory and go to directory 7. All right, and so if you're looking at the slides, we can specify the tolerance value by appending it to the command. And so in this case, for example, we could do AFLOW minus AFLOW SG equals, and then a numerical tolerance value. So in this case, we're doing it in angstroms. We also have the preset tolerance values that I defined earlier. And so we have tight and loose. And so you can, and this is if you have the, you calculate the minimum interatomic distance and scale it by 100, or divide by 100 for tight and divide by 10 for loose. And so if you just add this string to where the tolerance value should be, AFLOW will automatically grab that and determine what the tolerance value should be. And so this analysis is available for the commands listed here. I should have mentioned that earlier for some of the other analyses. So the crystal spin, I only showed AFLOW SG, but if you specify the magnetic moment for these other functions as well, it'll perform this crystal spin analysis for these different functions. Okay, so let's do an example. All right, so again, we'll use the README as our guide. So we're going to be changing the tolerance 3 times. We're going to use the default tolerance, then we're going to change it to 0.005 angstroms, then 0.001 angstroms. And we're going to run it on this particular postcard. And the question that we're going to ask is, are these consistent with the space group, subgroup, and supergroup relationships? So if you're familiar that some space groups are related to each other based on if you remove certain elements such as translations or certain point group operations, and basically they're subgroups or supergroups of one another. And so we're actually going to see, can we capture this just by changing the tolerance? And so again, I mentioned the 2 preset tolerance values that we have. Here's them written out. And then the following analyses can perform, the tolerance can be specified for these analyses. So let's see what we have here. So we're going to do AFLOW minus AFLOW, capital SG. And first we're going to do tight, as it said, so tight. So this is the default. And we're going to pass in the particular structure. We get space group 204. Now let's hit up on the keyboard and change the tolerance to 0.005. And then hit enter. And we see that the space group changed. So we're slightly lower. We lost essentially this body-centered nature. And then if we hit up again and change this to 0.001, we've lowered the space group even more to 195. And so if you're familiar with the symmetry subgroup relationships, if you look at space group 200 in the ITC, that International Tables of Crystallography, you would see that one of the supergroups, so it has more symmetry elements, and this space group 204 is actually a supergroup of this space group. And if you look at the subgroups of space group 200, you'd actually see that one of the subgroups is space group 195. So you can see that by changing the tolerance, we're able to capture this subgroup supergroup relationship just by changing the tolerance and including the relevant symmetry operations or adding or subtracting. But again, this is done automatically in a self-consistent way, so we'll always find a consistent space group. And so we also, of course, have the Python example or Python script. So if we go to the Python, and so again, we can do a similar analysis, same exact procedure, SG data, and then we specify tal equals either tight, 5 times 10 to the negative 3, or 1 times 10 to the negative 3. And so if we quit, and if we run the Python script, we should see the same exact results as before. And we do. So any questions there on changing the tolerance value? Okay, so no questions about this. So I think we have one more exercise that we'll do together. And then we're going to break off into the sessions, and we're going to do some slight variations of all of the exercises I've shown so far. So we'll go up one directory, and the last one we have is 8K path. And let's look at the slides. So we've already talked about this idea of the Brillouin zone and the high symmetry K paths. And so in session 1, we were calculating basically these by hand. So we went to the AFLOW Standards paper and determined what the different high symmetry K paths were when we knew the symmetry. So Corey gave us the symmetry. But now we want to, one, be able to calculate the symmetry and then have AFLOW spit out the relevant K path based on that symmetry. And so one thing I want to highlight is the AFLOW Brillouin zones. So there are 14 Bravais lattices and 25 Brillouin zones. And so there's 25 Bravais lattice definitions. And so this was a paper that Professor Corterola wrote with one of the postdocs at the time that basically determined the standard high symmetry K paths. And that's the paper that Corey showed. And so this is essentially the formula to determine the Bravais lattices and the 25 Brillouin zones. And so here are the different designations. And so if we scroll, you can see here are the different 25 Brillouin zones. And so I don't know if you've been to Wikipedia and typed in Brillouin zone, but if you actually do this, I guess maybe let's see if I can pull up a browser. Oh, right here. Okay, so if we go to, let's go to Google. So Brillouin zone. If we go to the Wikipedia page, you can actually see that these pictures look very familiar. And so you can actually see that the standard for Brillouin zones comes from this paper. And so you can see that these descriptions are used throughout the community and they're standard, and AFLOW can calculate them automatically. So this is a nice feature, and actually these Brillouin zones are used quite a bit. And so we can do this. I think Corey showed at the very end of his session that you can do this automatically with AFLOW. So we're going to revisit this. And so if you go into this directory, we'll cat the README. And so here, we're going to determine the AFLOW standard high symmetry K-point path, or K-path, for the magnesium oxide rock salt structure. So we can do this with the command AFLOW ---- K-path, excuse me, and we're going to direct the magnesium oxide rock salt structure. And before, we had to calculate this by hand. And so you can see that here it determined the standard primitive cell, and then this is the K-points file. So essentially, if you copy and paste this into the K-points file, this is what you would have had. And so this was a particularly nice example, and I think in some of the exercises we saw that some of these values depended on the lattice parameters. And so it was pretty tedious if you had to calculate these based on the different ratios of the lattice parameters. But again, AFLOW does this automatically. It analyzes the symmetry. It knew, or it calculated that it was FCC, and then it spit out the relevant K-paths. And so one other command that I want to highlight is maybe you want to know what the high symmetry K-path directions are for maybe ORC. So I think this will work. Maybe it was equals. Yes, so if you put BZ directions equals ORC, it will give you the generic path. One thing to keep in mind though is if you don't pass in a lattice, if some of these depend on lattice parameters, it's not going to be able to calculate it because you didn't give it a structure. So just keep that in mind, but if you wanted to know what the generic path symbols were, you can use this command. And okay, so then I think before we move to the exercises, I'm going to briefly go through the Python module and what it actually looks like. Because right now we've been taking it for granted that we just called some functions and then we're able to perform the analysis. So if we go up one directory and if we go into the Python module, we can see that we have this AFLOW-SYM.py, an example script, a README, and a test postcard. So let's look at the AFLOW-SYM.py. If we go through, we can see that here's the symmetry class that we've been instantiating. It runs the AFLOW command. So again, you need to have AFLOW installed on your machine to do this. And then these are the different functions. So get symmetry, this determines the symmetry operations. You can specify the tolerance or magnetic moment. Get E data is here. Again, you can specify tolerance, magnetic moment, and get SG data. If we exit here, there's an example script. We've already seen a few already. And then also, what's important is there's a README here. So if you open the README, I'll wrap. So here's information on the particular Python module. So it tells you certain requirements, basically how to work this. And then probably the most important part is towards the bottom, we have all of the different keywords. So here we can see that for the symmetry operations, we have the different keywords. for the Hermann-Maguin, Schoen-Flies, Quaternion matrix. For the SG data, if you want the different point group operations, Bravais lattice, Wyckoff positions. And so this is basically bookkeeping. So if you want to be able to use this in your own program, what keywords you need to call. And then an example Python script at the end. All right, colon Q. And so I think that's it for the Python module. And again, yes, here's just an example. Okay, so I think we have about a half hour left. I think that'll be good. I don't think the exercises will take you that long, but I'll briefly go through them and then we'll go into our breakout sessions and then we'll come back and wrap it up. And then we'll probably be done for the day. Okay, so what are we going to be doing in the exercises? So I'm going to open the exercises directory. And so there's 4 questions and there's 4 directories. So in this first, you're going to determine the space group and the Wyckoff positions for these 2 structures, an Argite and beta cristobalite, which you've already seen. And so you want to determine if you change the space group setting, does anything change? So is it a space group where you can toggle the different space group settings? Then you'll also change the tolerance and see if it changes the space group. For the second exercise, you're going to calculate the Bravais lattice variation of the crystal, the Lau class, the Pearson symbol for this TLF structure. And then what is the ratio between the conventional and primitive cell? And is it consistent with the Pearson symbol? Then you'll do another K-path example. And then finally, you'll do the AFLOW-SYM command. So you'll determine the symmetry operations for the zinc blende structure. And you're going to analyze these different operations. You're going to count the number of operations and you're going to perform, or you're going to determine what is the ratio between the cardinality of the factor group and crystal point. So I guess if there are any questions up to this point, please let me know. Otherwise, I think we'll go ahead and break out into the sessions. Okay, so I guess to wrap up, I'm briefly or very quickly going to go through the exercises, just highlight some important things, and then we'll wrap up and we might have a few comments about tomorrow. So, okay, so for the space group, we wanted to determine the Wyckoff and space group for these 2 structures. So if we do it for the Nargite postcar, AFLOW Wycar, so we see that the space group is 31. And so I know that this doesn't have a different setting. So even if you try to do a different setting equals 2, you'll notice that it doesn't change. And so this doesn't really have an option to. Oh, thank you, Krista. I was not sharing my screen. Okay, hopefully you can see it now. All right, thank you for pointing that out. So yes, I was running AFLOW Wycar setting equals 2, and you'll notice that if I run without it setting 1, and if I try to say, is there a setting 2, it doesn't calculate it because there is no setting 2 for this structure. But if you do it for the other structure, beta cristobalite, and we've already seen this one. So it's space group 227, so it's a centrosymmetric space group. And so we have this flip-flopping of the origin if we do setting equals 1 or 2. And then as for the tolerance, so it said, does the symmetry change? I tested a whole bunch of tolerances and I didn't see any difference. I don't know if anyone else saw any differences, but it seems like these space group or symmetry descriptions are fairly stable at a wide range of tolerance values. Okay, so that's 1. For 2, we wanted to find the lattice variation, Lau, and Pearson symbol. So you can do this with one command with AFLOW. It's the edata command. And it takes a second, but if you do this, we see that if we look here, the Bravais lattice of the crystal, the lattice variation is ORCF2. And so you might be wondering, what does this mean? So if you go back to the Brillouin zones, it's actually the variation here. So it tells us which Brillouin zone we would have to calculate for this system. And so I didn't actually label, unfortunately, but it's one of these Brillouin zones, and it's that particular variation. And then the next question was the AFLOW class. So if you scroll down, AFLOW class is here, and it's MMM. And so it's the same in this case as the crystal class. It's because this is a centrosymmetric point group, but if this wasn't, AFLOW always gives you the centrosymmetric version, so you might see a difference here. So again, this is more of a subtlety if you know more about the different crystallographic descriptions. And then the Pearson symbol is right above that, or a few lines up. It's OF8. And so the last question for this is, what is the ratio between the conventional and primitive cell? So if you go to the bottom, you can easily answer this by looking at the SCON postcard and the S-prim postcard. And so it's 8 divided by 2, so that's 4. But if you look at the Pearson symbol, if you're familiar with what the Pearson symbol actually tells you, if we look at this, so O stands for orthorhombic, F is for face-centered, and so typically the ratio between the conventional and primitive cell for face-centered centerings is 4. And so right off the bat, you could say, oh, that's the ratio between the primitive and conventional. And then 8 tells you that there are 8 atoms in the conventional cell. And so you could easily determine just from the Pearson symbol how many atoms would be in the primitive cell. So you do 8 divided by F, which is 4 in this case. So 8 divided by 4 and 2 atoms. So again, you might need to know about crystallography to know this, but again, this is something that AFLOW can calculate and tell you, and it's self-consistent. So directory 3 was pretty simple. It was just run the command. So AFLOW --k path and direct the postcard in there. And in this case, this was an RHL system. And so it gave you the paths. And I think this is one of the cases where it's dependent on the parameters. So if you were to have to do this by hand, it would be very, very tedious. So again, we did it in one command. And then the last exercise is the symmetry operations. And so we're going to do cat postcard, zinc blend, AFLOW --AFLOW-SYM. And so let's answer the question. So how many lattice point groups? So you go to aflow.pgroup.out, and right at the top, it tells you that there are 48 point groups. And how about for the crystallographic point group? So you go to aflow.pgroup_xtol.out. If you open it, there's 24. And then if you go to the F group, you can determine the number of factor group operations. And there's 96. And so the one question was, what is the cardinality between the factor group and the crystal point group? So again, this was 96 divided by 24. And again, this is 4. And so again, you can rationalize this basically based on question 2, what is the ratio between the primitive and conventional cell? And so again, we passed in the conventional cell here, which has 4 atoms. But if we wanted to know what the primitive cell was, we can do the conversion, if I spell it correctly. And we see that the ratio, again, is 8 divided by 2, so 4. So again, that's the rationale behind that. So were there any outstanding questions about the exercises, or does that make sense? So I think hopefully that makes sense to everyone. So the last thing that I'm going to end on for this session is the README. So like the other sessions, if you want to know more about the particular options and again, a review of the commands, you can run AFLOW --symmetry, or excuse me, README equals symmetry. I'm going to pass it to a file so we can read it. This will tell you all of the command line information. So there's the citation, the different commands, and then what the different commands do, and then basically the different options and their descriptions. So you can feel free to look at that on your own time. And then, so again, if you want even more information, you can feel free to visit the article that we published. This gives an overview of the different methods that I discussed and also an overview of symmetry. So if you want to learn more about symmetry, I would recommend going here and looking at the appendix.